Vanakkam to everyone. I am Revathi Chinnathambi from the Department of Physics at AGN Metric Higher Secondary School, Apputhotam, Konganapuram. In this session, I am going to discuss about the refraction of light through a concave lens. In other words, the image formation by the concave lens. Lens formula, sign convention, magnification of a lens and power of a lens. First of all, I am going to discuss about the refraction through a concave lens. Initially, I will consider an object at infinity. Already we know that object at infinity means the incident ray parallel to the principal axis. That means, according to the second rule, incident ray parallel to the principal axis means the refracted ray through principal focus. But the image formation by concave lens means the nature of the image is virtual. So that in the case of the concave lens, the image formation also at the same side that of the which side the object will be placed. Now I am going to draw the ray diagram and summarize it. Initially, I will consider an object at infinity. Then we need to draw the principal axis and then draw the symbol of concave lens. Then pointing optical center O and principal focus F and also center of curvature of a lens. Now I am going to consider one incident ray like this and one more incident ray like this. Tell me one thing. What is the nature of concave lens? That is diverging. The nature of the concave lens is diverging nature. That is why the refracted ray passing like this. And also one more refracted ray passing like this. Now I am going to mention the direction of incident ray and the direction of refracted ray. Now I want to remember that second rule of image formation by the spherical lens, that is, the incident ray parallel to the principal axis means the refracted ray passing through the principal focus. Already I told that the image formation by a concave lens means we will get the virtual image. That means the image formation of the concave lens at the same time of in which side the object will be present. And the second incident ray parallel to the principal axis and refracted ray also through principal focus. Then original refracted ray diverging from the lens. Then I am going to summarize it. See here. The position of the object initially at infinity, therefore the incident ray through the lens parallel to the principal axis. The position of the object at infinity, so that the position of the image at f. The position of the image at f. And the size of the image highly diminished, that means very much smaller. The size of the image very much smaller when compared to the size of an object. And already we know that the nature of the image, that is virtual and erect image. In case 2, the object placed between infinity and optical center O of the lens. Initially I will draw the ray diagram. That is first optical axis, then symbol of the concave lens, okay. Already I told that the object anywhere between infinity and optical center O, then first marking optical center O, then principal focus F, and then center of curvature of the lens C. Now I will consider the position of the object between F and C. This only object, then one incident ray parallel to the principal axis and one more incident ray through optical center O. Incident ray parallel to the principal axis means the refracted ray through principal focus, and the incident ray through optical center O means the refracted ray traveling the same path without deviation. Now I am going to point out the direction of the incident rays and the direction of the refracted rays. Now the position of the image between O and F. O and F. Object AB, so that the image A dash, B dash. In the case of concave lens, we will get virtual and erect image. That is what the head of both object and image at upward direction and the tail of both object and image on the principal axis. Now I am going to summarize this second case. Whenever object placed between infinity and optical center O of the lens, the distance of the object reduced towards the optical center means the distance of the object reduced towards the optical center means the position of the object coming from the infinity towards the optical center means the position of the object will be reduced, so that in this case also the image formed in the same side, the image formation in the same side so that the nature of the image virtual and erect image. Now I am going to summarize this case. the position of the object between infinity and optical center O. Between infinity and optical center O, then the position of the image between F and O, then the size of the image is smaller. The size of the image is smaller when compared to size of an object. This is size of the object somewhat higher when compared to size of the image. The nature of the image virtual and erect image. The image formation at the same side of where the object will be placed means the nature of the image virtual at the same time erect image. That is what the head of the object and image in upward and tail on the principal axis. I am going to explain the various position of the object from infinity to optical center and compare the position of the image and size of the image. Principal axis, just listen the methods to draw the ray diagram. Then symbol of the concave lens, and marking optical center O and principal focus F and also center of curvature 2F. Then position of the object between C and F. Like that, I am going to consider the position of the object here. This is position 1. Then the image formation between F and O. This is first image. Then I am going to consider the position of the object closer to the F at the same time between 2F and F. This is second position of the object, and the image formation also somewhat towards the optical center at the same time between F and O, and also the size of the image somewhat higher. one more position I am going to take for an object. This is position of the object 3 and image formation between F and O, and also towards the optical center of the lens. At the same time, the size of the image is somewhat higher. These are the different positions of the object. According to these positions, we can able to get the position and size of the image like this. This is first position of the object. This is image of that first position, and this is second position, and this is second image. This is third position, this is third image. From this we can understand well the position of the image will be moving towards the optical center from infinity, means the image formation also towards the optical center. At the same time, the size of the image will be increased whenever the object placed towards the optical center. That means the distance between the object and the lens decreased. Object and the lens decreased. The distance between the image and the lens also decreased. But the size of the image increased towards the lens. That means position of the object towards from infinity to the lens. In this session, just we will see the lens formula. Lens formula gives the relationship among the distance of the object U, distance of the image V, and focal length of the lens. That is 1 divided by F is equal to 1 divided by V minus 1 divided by U. Here object distance means this distance, the distance between the object and a optical center, and image distance means the distance between image and a optical center of the lens. That means every measurement should originate from optical center of the lens. This formula applicable to both convex and concave lenses in all situations, but while solving the numerical problems, we need to apply proper sign convention for different quantities. One more information, according to the sign convention, the focal length of a convex lens is positive and the focal length of the concave lens is negative. Next, we will read about sign convention for understanding the sign convention. Cartesian sign convention are used for measuring the various distances in the ray diagram of spherical lenses. This only Cartesian coordinates. This is direction of plus x, and this one direction of minus x, and this is direction of plus y, and this one the direction of minus y. According to Cartesian sign convention, object is always placed on the left side of the lens. What is that? The object always placed at the left side of the lens. This is lens and object placed at a left side of the lens. All the distances are measured from the optical center of the lens. Already I told that all the measurements originate from the optical center of the lens. In case the distance of object means from here into optical center, and the distance of image means from optical center into distance of the image. The distances measured in the same direction as that of the incident light are taken as positive. This is the direction of incident ray, means the distance measured in the same direction, in this direction. In this direction means the distance considered as positive value. And the distances measured against the direction of the incident ray light are taken as negative. Against the direction of incident ray means opposite to the direction of incident ray, that is considered as negative. The distance measured upward and perpendicular to the principal axis is taken as positive. The distance upward, what is that? Upward, this only upward direction, at the same time perpendicular to the principal axis. This is perpendicular to the principal. This is principal axis. This upward direction only perpendicular to the principal axis. That means what we can understand in this Cartesian coordinates means the measurement along plus x means the value will be positive, and along minus x means the value will be negative, and the measurement along plus y means the value considered will be positive. And one more thing, the distance measured downward and perpendicular to the principal axis taken as negative. That means the distance measured downward and perpendicular to the principal axis means that value considered as negative. Here the distance measured along the minus y means the value will be negative value. One more time I will repeat. Initially we will imagine that Cartesian coordinates, the direction of incident ray along the plus x. So that is why the measurement along the plus x means all the values will be positive. The measurement against or opposite to the direction of plus x means that is minus x. That measurement will taken in negative value. The measurement upward and perpendicular to the principal axis means that is positive value, and the measurement downward, that means perpendicular to the principal axis means that is negative value. These are the sign convention should apply whenever we are going to solve the problems in the case of lenses. Now I am going to talk about the magnification of a lens. Magnification of a lens. Just I am going to define the magnification of lens with the help of a ray diagram. That means magnification of a lens is defined as the ratio of the height of the image to the height of an object. Suppose if the height of the object h and the height of the image will be h dash, means then the magnification of a lens is represented in the form of height of the image divided by height of the object. In this case, I will interested to tell one thing, that is for every tool or every instrument, the efficiency of the tool will be output divided by input. In this case, I am talking about concave lens, and generally magnification of the lens also. Then magnification of a lens means here the height of the image will be output and height of the object will be input. Therefore, we want to determine the magnification of the lens means the height of the image divided by height of the object. That is nothing but height of the output divided by height of the input. In other words, the magnification of a lens represented in letters small m, that is equal to h dash divided by h. And one more relation is there, that is the magnification of the lens is related as magnification of the lens is related to the distance of the image and the distance of the object. Suppose if the distance of the object u and the distance of the image v means the magnification is represented by magnification is equal to distance of image divided by distance of the object. That is nothing but small m is equal to v divided by u. There is no unit for magnification because of the distance of the image measured by meter. So meter divided by and the distance of the object measured in meter. Therefore anything divided by the same thing is equal to 1. Then remaining 1. There is no remaining unit. That is what there is no unit for magnification. And also if the magnification is greater than 1, we get an enlarged image. Enlarged image. At the same time, if the magnification is less than 1, we get a diminished image. Diminished image. Enlarged image means the size of the image very large when compared to size of an object, and diminished means the size of the image very smaller when compared to size of an object. I want to match this distance and height with the ray diagram. That means first definition, according to first definition, the magnification of the lens is defined as the ratio between the height of the image to height of the object. This is height of the image, this is height of the image. As per second relation, the magnification small m represented as m is equal to v by u. That means distance of the image. This is only the distance between b dash and o, only distance of the image, that is b dash o divided by object distance, that is from b to o. That is b to o. The distance of the image measured in meter and the distance of the object in meter. So remaining 1. Therefore there is unit for magnification. Now I will discuss about power of a lens. Power of a lens. When a ray of light is incident or fall on a lens, that means whenever light incident on this lens or fall on this lens, the ability of converge or diverge these light rays depends on the focal length of the lens. As per definition, the power of a lens is defined as the degree of convergence. The degree of convergence, that means in the case of concave lens, the incident ray will get divergence. Then the angle of divergence, this only power of a lens. Or degree of divergence of light rays. In the case of concave lens, the incident ray gets divergence. This is the origin. This is the angle of divergence. That means the power of a lens can be defined as the degree of convergence in the case of convex lens, or the degree of convergence in the case of concave lens of the light rays. And the power of a lens is numerically related as the reciprocal of its focal length. What is meant by focal length? To determine the focal length of the given lens, I am going to demonstrate one experiment. I am considering screen system and a lens system. I will keep a lens on this lens stand and taking screen like this, and these two keeping some distance, and I will focus a tree from the outside. Tree from the outside. We are getting clear image of the tree. It is visible for you. Clear image of the tree on this screen. Now the focal length of this convex lens is determined between the distance of screen and this lens system. This only gives the focal length of this convex lens, that is equivalent to 20 centimeter. Now the focal length of this convex lens is 20 centimeter. Excuse me. Already we know that the power of the lens is numerically equal to the reciprocal of its focal length, that is nothing but P is equal to 1 divided by F. Then the unit of focal length, the meter, that is represented in the symbol of small m. Then this m goes to index notation, means m power minus 1. The unit of power, meter inverse, practically it is denoted as diopter. The unit of power is diopter, in other words meter inverse. Now I am going to define diopter. One diopter is the power of a lens whose focal length is 1 meter. That is 1 meter inverse is equivalent to 1 diopter. By convention, the power of convex lens is positive. By convention, power of convex lens is positive because of the focal length of the convex lens positive. Already we have studied that. By measurement, suppose I will take a convex lens. For example, the focal length of that convex lens 15 centimeter, that is converted into meter, means 1 divided by 15 into 10 power minus 2 meter. That means 1 centimeter is equal to 10 power minus 2 meter. Therefore 1 divided by 15 in 10 power minus 2 is nothing but 0.15 meter. Then converted into meter inverse or in the form of diopter means 6.667 meter power minus 1. This meter goes to numerator, means meter power minus 1. That is nothing but 6.67 diopter. And also by convention, the power of a concave lens is negative. Power of a concave lens is negative because of focal length of the convex lens is negative. Concave lens is negative. For example, I will take a concave lens. This is a concave lens. The focal length of this concave lens 10 centimeter means the power of that concave lens P is equal to 1 divided by 10 centimeter. That means 1 divided by 10 into 10 power minus 2 meter. In other words, 1 divided by 0.10 meter. That is nothing but 10. This meter goes to numerator, means meter power minus 1. That is nothing but 10 diopter. Now this power of this concave lens is 10 diopter. Thank you for listening.